Hey, welcome back. We're going to kick off with or continue on with the circulatory system. This time, we're going to start by talking about the blood vessels. As you can see, we've got a couple of different blood vessels. We like to say that there are three different categories, but honestly, there are five different kinds of blood vessels that we are going to be interested in. Starting off with the arteries, arteries are coming away from the heart, they're taking blood away from the heart. Those arteries are going to eventually split into smaller vessels. We call those arterioles. So those are those really small arteries at the end here. Those arterioles end up becoming the smallest of the blood vessels called capillaries. That's in this middle section, and that is where the gas exchange is actually going to happen. And that's how we're going to get things into or out of our blood from various parts of our body. And then we turn those capillaries into venules, which are these very thin veins at the end of the capillaries, which all join together and turn back into veins. Now, you got to be careful with the colors of the arteries and veins. The colors don't represent the blood vessels, they actually represent what's inside of the blood vessels. Red typically indicates that we are in an oxygen rich environment. Blue tells us that we are in an oxygen poor environment. So it doesn't mean that red is an artery, that is wrong, and blue isn't always a vein, that is also wrong. Case in point, in your heart, your pulmonary artery will be blue because it has oxygen poor blood. Your pulmonary vein will be red because it has oxygen rich blood. The only part that will always be the same are the capillaries in the middle because they're a transition between the two. So they'll always have their own unique color. We like to use purple because that's the transition between red and blue. Now, as mentioned, your arteries, they will narrow into what are called arterioles. And arteries are a unique part of the blood vessel network because they are experiencing the full pressure from the heart. They're taking blood away from the heart. Because of that full pressure, they end up being elastic. That allows them to stretch a little bit, which can be okay. It's useful for getting through clots, for example. The problem is that if you have high blood pressure, you might put a lot of stress onto your artery system or your artery network, and that can cause potentially ruptured arteries or damage to your circulatory system. Your veins and venules take blood back to your heart, but because they're a little bit further removed from the immediate connection to your heart, they tend to have these valves to protect or protect your system from losing the blood in the veins. That keeps the blood from going backwards. Those valves are all one directional, so blood is pumped upwards, usually from the bottom half of your body upwards towards your heart, and then they're held in place by the valve so that you don't end up losing that blood in other parts of your body. Now, you can, if your valves get damaged, you could end up with having blood pooling lower on your limbs, but that is a condition if you have, say, high blood pressure or a situation of being overweight or some other genetic defect which could cause damaged valves. Now, the third piece or fifth piece, depending on how you look at it, is the capillary, which is right down in the middle in between arteries and veins, or more specifically between arterioles and venules. This is where that exchange of materials is going to happen. It's a very, very thin vessel. It's so small that red blood cells can only pass through in single file. It's very, very thin, but that maximizes the capability of that exchange happening at organs or muscles or other parts of your body. And altogether, that allows us to see our circuits for our circulatory system, hence the name circulatory system. We have a pulmonary circuit which connects the right half of our heart to our lung system here. That allows us to refill on oxygen and dump out some carbon dioxide. The left part of our heart connects to the systematic circuit, that is pumping blood all throughout the rest of our body. Then we can get into the blood itself. The blood is that stuff that I'm sure you've seen at some point. Maybe you've given blood or you've had a blood sample taken at the doctor's. You've seen it, this red goopy liquid, but it's actually got different layers, it's got different substances. If we can separate those, we can analyze each of them individually. First off, more than half of your blood is made of what's called the fluid portion. We like to call this the blood plasma. That's typically this clear liquid. It's often actually like it looks like water, basically, maybe a slight yellow tinge. It contains proteins, sugars, other minerals, other products in there. All your waste products are going to sit around in your plasma as well. Beyond your fluid portion, there are two other components, your red blood cells and your white blood cells. That's going to make up the solid portion of your blood network. The red blood cells are going to help They're going to help you with retaining that oxygen and carbon dioxide. The white blood cells are part of your immune system. And then there are these little small cell fragments called platelets in there, which are going to help with clotting mechanisms. We should talk about each of these separately, though, so that we can understand them. The image of the tube on the right is actually a blood sample. You can get your blood to look like this. If you have a centrifuge, it will separate the various components of your blood, and that allows you to analyze very specific portions of the blood. So plasma, for example, that's that clear liquid, slightly yellow tinge. It's mostly made up of water. Like most things in our body, it's mostly going to be made up of water. We've also got a couple of proteins in there to help us with maintaining that fluid between the plasma, the cells, the little spaces in between the cells. We've also got protein to help us manage the pH. And then we've got a whole bunch of salts. Also, some of these salts are there to help us keep a slightly basic pH. Those salts are there to help communicate with the nervous system. We've also got some calcium in here to help us with clotting mechanisms, which we're going to talk about shortly. We get into the red blood cells. A special name for red blood cells are erythrocytes. We're interested in calling them erythrocytes. They make up just under half of your solid portion, or half of your blood in total. And these are going to help you transport the oxygen from place to place. Now, the nice thing about the oxygen is that it's being retained by hemoglobin, which is a special molecule that can latch onto oxygen very well. We have hemoglobin in our red blood cells to help us carry that oxygen for us. If you have a slightly older red blood cell, it doesn't have any nucleus, which is strange compared to the other cells we looked at, but you replenish approximately 2 million of your red blood cells every second. So you tend to have quite a lot of red blood cells that do not have a nucleus at a time. You always have more red blood cells than white blood cells. Also, red blood cells are given the name because of their color. They don't look the same as white blood cells, just red blood cells are a different color. They also have a very unique shape, especially us being mammals. We have this biconcave disc. If you look at these cells individually, you can see it looks like they're indented in the middle. That is just to give us two things, either or both the larger surface area for gas exchange. It also allows them to be round and smooth, which allows them to bend around corners without clustering or clotting, considering our blood network is a whole bunch of twists and turns. White blood cells, on the other hand, they're significantly larger, and there's different kinds of white blood cells. We call them leukocytes, so erythrocytes for red blood cells, leukocytes for white blood cells. We'll look at these in more detail when we talk about the lymphatic and immune systems, but there are different kinds of white blood cells that we should be able to recognize. One, that they are granulocytes. Two, that they're agranulocytes, and that's just the shape of the cell. When you look at them under a microscope, granulocytes look like grains, agranulocytes look very smooth, like smooth cells. They don't make up a lot of your blood volume, but if you're ill, for example, and your white blood cell, your immune system is active, you might have a slightly larger portion of these in your system at the same time. To list them off, we got each of those five listed here. Again, we're going to get into these in more detail when we talk about the lymphatic system later on. But neutrophils, you'll find those mostly in your white blood cell network. You've also got eosinophils, which are in your mucus. That's what changes color when you get sick. We got basophils, these flag foreign agents allowing you to call in phagocytes to dissolve them from the inside of your body. Lymphocytes, we're interested in these to produce antibodies for us. And then we have monocytes. They just float around, and if there are any bacteria in your system, they can help us destroy those if necessary. Those white blood cells move through our interstitial fluid. They're often floating around in blood plasma. As mentioned, we've got the three granulocytes, which look grainy in the cytoplasm. We've also got the two agranulocytes because it looks smooth. Lastly, we've got these guys called platelets. Platelets are often also referred to as thrombocytes. So we've got erythrocytes, we've got leukocytes, and now we've got thrombocytes as well. These are very small cell fragments, but they have a clotting feature that helps the blood keep itself inside of our body if there's ever an injury. The platelets can release a chemical called thromboplastin, which, if you have a decent amount of blood calcium, can react to create fibrin, which is a mesh that covers up your wound. So if you ever have a cut, for instance, like a paper cut, you might start to bleed a little bit, but very quickly that wound gets covered up and you get a little bit of a crusty scab over top. That is a fibrin covering up your wound, preventing that injury from being worse than it actually needs to be. If you ever have a large wound, we might need some additional help. Like we might have to stitch you back together until your fibrin can cover your skin up. And then through mitosis, you're able to replenish your skin. But the fibrin is a self help feature. We do have to be careful with fibrin, though. If you're on blood thinners, for instance, you have fewer amounts of platelets, so you can't produce as much fibrin. If you can't produce as much fibrin, then a person is at risk of bleeding a lot more than it normally would. So we got to be careful when we are giving someone medications like blood thinners because that could cause some issues if they're in a line of work, for instance, where they do bleed a lot. If you're a carpenter, for instance, and you're cutting yourself on a frequent basis, you probably don't want blood thinners unless you're out of work for a while or you have a very special type of blood thinner. So just the components, again, we're not too concerned about the various components here. Not too much anyways. We're just mostly interested in the relative size. So know that platelets are significantly smaller than red blood cells, and white blood cells are the largest of the three different kinds that we looked at. And then that's going to bring us to the function of the blood. What does the blood actually do? Well, we know that it's transport, but what does it transport? How does it transport? Depending on where you go. If you go towards digestion, we know that we eat food, it gets into our stomach and then into our small intestine, and then it gets absorbed. But where does it go after that? Well, some components, once they are absorbed, things like glucose and amino acids, that's going to be sent through our blood system. So they're absorbed through the villi, microvilli. They go into our capillaries and then head over to our liver for a first check, just to make sure there's nothing there that shouldn't be there. You also got various chemicals that come from our respiratory system. So you breathe in, you have gases in your lungs now. Those gases get transported into your blood through very specialized cells. Those are things we're going to talk about, though, when we get into the respiratory system. And then we've got waste products. So whenever your cells produce waste, well, if your cells are adjacent to a capillary network, we can dump our waste off into our blood network, and then we can dump those wastes off either into a digestive format or into our kidneys, our urinary system, and get that filtered out of our system. Two components that we can find in our blood. Well, we got to be careful with the temperature regulation. We can vasodilate and constrict, which we talked about when discussing homeostasis. A few things that can cause your blood to dilate or your blood vessels to dilate are things like high blood pressure. If you dilate your blood vessels, that allows the blood to flow more easily. So it alleviates some of that blood pressure, but it does make you feel a little bit cooler because you're dumping out that energy a lot more quickly. Increased activity as well, same idea. If you're moving a lot, you need a lot of cellular respiration, you're going to need to cover that cellular respiration by getting more oxygen, pumping more blood through your system. It might be easier to move blood through your network if you are vasodilating. A couple of drugs and substances can also influence vasodilation. For instance, a person drinks alcohol, they tend to feel warm immediately after, and that's because they've dilated their blood vessels, so they're feeling the energy being lost by the system or lost to the system. Or if you've ever seen here in Manitoba, especially you drive up to Winnipeg, if you look around in the wintertime when it's like minus 30, outside of certain workplaces, you always see people smoking cigarettes. And it's like, why are they smoking cigarettes? It's too cold. Well, that's because there's nicotine in cigarettes. And that's another thing that makes your blood vessels dilate. And that gives you the sensation that you are feeling warm when honestly you are just losing that energy. The opposite is also true with vasoconstriction. If you're feeling too cool, we might want to suck those vessels in to conserve energy. That could be because of low blood pressure, or that could be because you're just sitting watching a video on YouTube right now. That might be a reason why you feel a little bit cooler because you don't have as much activity in your system right now. Another way of looking at it, I got a couple of images here. You have vasodilation up at the top. You can see you have a lot of networks of blood vessels close to the surface of your skin, so you lose that energy to the environment. Or if you constrict, you can still send blood to these blood vessels, but more likely you're going to stay deep to the inner part of your body, so you don't lose as much energy to the system itself. Another way of looking at it is how you can see deep arteries transferring heat to deeper veins, to surface or superficial veins. That helps your body release that energy. That way, our internal temperature can be around 37 degrees Celsius, but our external or surface temperature is closer to the actual room temperature that we're in. One caveat to that is at your extremities where your arteries become veins, where you only really have capillaries like your fingers and your toes. This is why your fingers and toes feel cold. even though you're in bed, for instance, because there is no way of transferring that energy to a deeper part of your body. They're so exposed to the outside environment. And that's going to bring us to monitoring the circulatory system. We are going to pause here for this video and we'll pick up on the monitoring for the next section. I think there's at least one more, maybe two more sections after this, but then we'll be done with taking a look at the circulatory system. So just to review, so far you've seen that we're talking about a transport system and there are three components: the heart, the blood vessels, and the blood that we should be aware of. We should know what goes and makes up all of these. We should understand the flow of blood, and we should understand that there are other smaller pieces to each of these components. So blood vessels have 5 different types of blood vessels, but why are they the way that they are? These are all things that we should be aware of. Anyways, I'll catch you guys in the next one where we'll talk about monitoring the human circulatory system, and maybe we'll take a look a little bit later on at diagnosing diseases and that sort of thing as well.